Our work, called Learning Treatment Effects from Observational and Experimental Data, tries to predict post-intervention outcomes using observational and experimental data. Our motivation comes from clinical decision making, where we often want to use all the data we have available to predict the post-intervention outcomes of our patients and make our decision based on these probabilities of post-interventional outcomes. So, for example, we may want to predict the chance of in-hospital mortality for a patient if we give them steroids versus if we don't give them steroids. In doing that prediction, we often have access to different data sources, like, for example, observational data, usually electronic health records. These come in large sample sizes and they measure a large sample of covariates, but they are possibly biased for causal effect estimation. And then we also have experimental data, like randomized controlled trials. Usually these are much more limited in the sample sizes they measure and the number of covariates they measure very often. But they are unbiased for causal effect estimation. So we want to combine the two to get the best of both worlds. The scenarios where our method is applicable is we have a treatment, like, for example, here we may want to give a patient steroids or not. We have an outcome that we want to compute probabilities for, like here, for example, in hospital mortality. And then we have some covariates we measure, like diabetes and blood pressure. And there are also other covariates that we don't measure, like lifestyle and genetics. All of these covariates are pre-treatment, and we want to predict the probability of in-hospital mortality for our patients if we give them steroids versus if we don't give them steroids, for example. The way we phrase the problem is as a feature selection problem. So we want to know which variables should we include in a model to get the best prediction of in-hospital mortality given due of steroids. So essentially we want to compute a post-interventional probability distribution. And the reason why this is not straightforward is that sometimes post-interventional probability distributions are not identifiable from observational data. So we have our outcome and our treatment and our pre-treatment covariates, and we have observational data measuring all of that for a lot of samples, and then experimental data measuring our treatment, our outcome, and possibly a subset of these covariates for a number of samples that we assume is much, much smaller than the observational data, because that's what happens usually. And we want to find the best set, the set that optimizes our prediction for y given due of x. Let's call this set z prime. The idea that we had is that if we knew that the probability of y given due of x comma z prime was identifiable from observational data, so if z prime was an adjustment set, then we want to use both the observational and the experimental data to improve our estimate of y given due of x comma z prime. Otherwise, we only want to use the experimental data in this estimation. But how do we know if z is an adjustment set or not? So for every set z, we can define two alternative hypotheses, two complementary hypotheses. One is that z is an adjustment set. We call this hypothesis HZA. And the other is that z is not an adjustment set. Let's call this HZA bar. These two are obviously complementary, so only one of them can hold. If HZA is true, so if z is an adjustment set, we can use the observational data to estimate the probability of y given due of x comma z. And if HZA bar holds, so if z is not an adjustment set, then we can not use the observational data to estimate the probability of y given due of x comma z. And then the idea is to compute probabilities for these hypotheses, and then for each of these hypotheses we will have some different estimates. One will be from the observational data and the other will be from the experimental data, and we will take the weighted average weighed by the probabilities that z is an adjustment set or not. So basically we want to compute this probability, the probability that z is an adjustment set based on the observational and the experimental data, and the probability that z is not an adjustment set based on the observational and the experimental data. And these are proportional to the probability of seeing the experimental data given that z is an adjustment set, and having seen the observational data, or given that Z is not an adjustment set and having seen the observational data. So if we take this probability and we integrate over all possible parameters of the post-interventional distribution, then this will become sort of a marginal likelihood. For every set of parameters, we have a density of these parameters given the observational data and given the fact that Z is an adjustment set. And then this will be multiplied with the likelihood of our experimental data given these parameters. And under the assumption that Z is an adjustment set, the observational and the experimental parameters is the same, so we can get this density using the posterior for these parameters given the observational data. And this will just become a marginal likelihood where the density of the parameters comes from the observational data. If Z is not an adjustment set, then we cannot use essentially the observational data to get a posterior for these parameters, because you cannot compute point estimates for these parameters using the observational data. So we just score. We use a uniform or a flat prior for these parameters. We also allow in our method for some of the covariates to not be measured in the experimental data, to only be measured in the observational data. And in this case, we can still score the experimental data using the observational data. The parameters will be the parameters for the variables that are just in the experimental data, but we can get a posterior for these parameters using the adjustment formula, essentially. And then once we've done that, we can compute the estimates for every different Z. We can compute an estimate for the post-interventional distribution of our outcome given do of X, Z, right? And then we need to just select the best Z. And the idea is that for every Z, we have an estimate for these parameters for predicting Y given do of X. And we can essentially estimate, select the best Z by estimating the Z that maximizes some performance, some expected performance according to some performance metric. So here, for example, we used log loss, and assuming that we have a multinomial distribution, and we can compute the expected log loss and select the Z that optimizes this performance metric. We have some other performance metrics in our paper as well. Ideally, what we want our method to do is we want our method to be able to identify automatically whether it's okay to use the observational data or not, and do that. So here, for example, we have an example where we cannot use the observational data. We have an example where Z is a confounder and it's not measured in the observational or the experimental data. So ideally, what we'd like to do is we'd like to use the experimental data and estimate the probability of Y given do of X, W in order to predict Y given do of X. And we can see in the graph, our method is called overlap, and we compare it against OMB, which is using the Markov boundary and the observational data alone, IMB, which is using the Markov boundary and the interventional data alone, the experimental data alone, and then find IMB uses all data to find the causal graph, and then identifies the Markov boundary of Y in the causal graph. The Y-axis is essentially the bias introduced by Z, and then the Y-axis is the difference in log likelihoods from our methods, our predicted probability using our method, and the ground truth probability distribution. So essentially here, lower is better. And we can see that in this scenario, we perform best along with using the experimental data and using the graphical method. And using the observational data, obviously, the higher the bias, the worse it performs. And then if the scenario is slightly different, then we don't have this hidden confounder, so we are measuring Z in both the observational and the experimental data, but let's assume that W is only measured in the observational data. So ideally what we'd like to do is we'd like to use the observational data and include W, right? Because W gives us some predictive power for Y given do of X. And here in the Y-axis we see essentially the difference in the distributions if we include W versus if we don't include W, and then the Y-axis is the difference in log likelihoods. So here again lower is better, and here we can see that using the observational data performs best, and our method also performs best. Using the experimental data and using the graphical method we cannot include W in these scenarios, so these perform worse as the difference in the distribution grows. So essentially, to summarize, we believe that combining observational and experimental data can improve treatment effect estimation. This work has been highly motivated by randomized, embedded, multifactorial adaptive platform trials, which is a type of trial that happens in the hospital system. So there, the populations in the observational and the experimental data are very similar. This is not always true, so our next step is we want to use the causal graphs to model the possible differences in observational and experimental populations, so we can apply this in a wider range of scenarios and data sets.